Hello everyone. Today class number 32 for electrical machine 2. Class number 32 for electrical machine 2. Okay. So in this class I will complete the acceleration system of the stator part of three-phase synchronous machine, and the last one, that is the third type of the acceleration system called brushless excitation system. So in this case there is no brush, that is contact drops are negligible or zero, right? So for this case what happened? So some block parameters are installed, right? Permanent magnet rotor plus stationary armature. This is permanent, right? Permanent magnet rotor plus stationary armature. Okay. So it will be solid shaft. So through this solid shaft, so another system is stationary rotor plus rotating armature. Stationary field plus rotating armature. And this one also have this common shaft. So this is all have some common shaft. Okay, so this is hollow shaft. So through this hollow shaft, rotating rectifier mounted on the shaft. Rotating rectifier mounted on the shaft. Rotating rectifier mounted on the shaft. Okay, so then it will be connected through the hollow shaft to the rotor of the synchronous machine. Okay, so this rotor of the synchronous machine can be represented by three-phase balance system, right? Through this three-phase balance system, and one of them is connected by a current coil and another two phase is connected by the potential coil. See, this is PT, this is CT. Okay, current coil and potential coil. So through this current coil and potential coil, it will be supplied by a regulator. Okay, so this PT is coming to here and CT also coming into the regulator. Okay, so this regulatory output will used as, this is three phase. So this is called three phase fully controlled bridge rectifier. Okay, so in your power electronics rectifier, in your power electronics subject, you will understand in detail what is the three-phase fully controlled bridge rectifier. Okay, so this regulator, through this regulator, it will be apply the gate signal. Okay, so through this gate signal, it will be connected in between this terminal to the that terminal. Okay, so by this way we can excite the field system. We can excite the stationary armature system of the, this is a stationary armature system of the stationary armature system of the three-phase synchronous generator. Okay, so this is the input. Okay, this is the input. So okay, input is prime mover. Prime mover produces the input to this type of machine, and through this machine a power is transferred to here, and again power will transfer to here, and it will be finally transferred to the rotor part. Okay, and simultaneously it is rotating, right? This section is rotating, right, through these three modules. Okay, or through these three sections. Okay, so when it is moving, and there simultaneously it is required to generate the field flux, right? So or to generate the armature flux. Here it is armature flux. Okay, so to generate the armature flux we have to excite the field system. So in order to excite the field system we have to rotate the field part by a controlled manner. Okay, so this controlling is done by using this three-phase control bridge rectifier, which is connects in between here to here, and by the feedback signal coming into the stator part through some regulator portion, and it will apply as a gate signal. Okay, so it will apply as a gate signal. So this is the gate signal. This is the gate signal to the bridge rectifier. Okay, so it is a process of excitation to excite any armature system. Okay, so there are three types of excitation systems are there. So right, brushless exciter is more efficient. Brushless exciter is more efficient than any other type of exciter system. And it is mostly advanced. System. Okay, it is mostly advanced system. Okay, so brushless excitation system is now completed in this lecture, and I will move into the next topic, that is okay, right, the flux and EMF phasor diagram of a cylindrical pole alternator. Flux and EMF phasor diagram of an cylindrical pole alternator. Okay, flux and EMF phasor diagram of cylindrical pole alternator. So there are many cases. So first case 1, right? First case 1, when alternator is at, right? When alternator is at no load condition. So when alternator is at no load condition. Okay, so when no load condition, then what happened? Then the IA equals to 0. Okay, that is IA, armature current is 0, and armature EMF is also 0. Okay, armature current and armature EMF both are 0 when there is no load. Okay, so that means phi of A also 0, armature flux is also 0, armature flux equals to 0. So the rated EMF is produced. The rated EMF is produced. So there no reduction of the EMF generated due to any loading effect. Okay, so when the load is present, then the EMF will have some reduction. Okay, so it has some reduction, right? So when there is no load, that means when there is no current is flowing through the armature, then we can say that the EMF is produced, rated EMF. Say rated EMF is EF is produced. Okay, and then write induced EMF EF lags behind the 90 degree the flux phi f in time. So this EF is lags behind the phi f by angle 90 degree. So EF lags the flux EF phi f by 90 degree in time. That means if we want to express that the phasor diagram, that is EF I am writing over here, so phi f will be coming into here. Okay, so this phi f and this is ff. Okay, this phi f is equals to phi f is in same phase of ff and ef is 90 degree lagging behind these two. Okay, so 90 degree lagging behind these two. So ef is nothing but the output. Okay, and this phi f is the flux generated inside the air gap and the mmf is inside the air gap. Okay, so these two are the cause and this is the result. Okay, and which are 90 degree apart from each other. Actually always remember, as the synchronous generator is a lagging power factor, or it has inherently internal power factor lagging in nature, that's why we can see that for a no load condition there is no effect on effect of load on this output voltage. Okay, so that means EF will be 90 degree lags behind these two factors. Okay, for this and there is no IA, no IF, no FA and no phi A will present. Okay, so this is the case number A, the phasor diagram for case number A. Okay, so now case 2, I will move into the case 2, second case. Case 2, right? When alternator is at unity power factor, when alternator have unity power factor load, UPF, that is the unity power factor. Unity power factor means what? Unity power factor means cos theta equals to 1. Okay, so load, what is connected, whatever the load is connected, it is purely resistive. Okay, that means Z equals to R, impedance, load impedance equals to load reactance. Okay, for that case Z equals to R, so right, the armature current IA will be in same phase to EF. The armature current IA will be in same phase or in phase with EF, right? So this is the most important concept when it is a unity power factor. That is, the armature current is in same phase of EF, because through this armature the load is connected. So that's why when the EF and IA is in same phase, that means the power factor of the load along with the armature will be unity. Okay, so that for that case IA and EF are in same phase. Okay, so that means phi A comma FA and IA all are in phase with EF, right? And always EF lags behind the FF and phi F by angle 90 degree. This is all time true. Okay, so if we consider EF over here and phi F over here and FF over here, so the armature current FA and phi A will be, suppose this is IA, this is phi A and this is FA. Okay, so the resultant flux of these two will be modified by, suppose this FA and FF is modified by an vector, okay, this one and that one, and similarly phi A and phi F is also modified by some angle. Okay, and so this is the flux, modification due to the loading effect, of unity power factor connected in the generator or connected in the armature. Okay, so here write there is a loading effect which assists the generated field, which assists the generated flux, right, which assists the generated EMF also. Okay, so there is a assistance, there is a assist of the generated EMF due to the loading effect for unity power factor. Okay, so this is case number 2. Now I will move into case number 3. Case 3, right, when alternator is at 0 power factor lagging, that is when alternator is connected with 0 power factor lagging, that is 0 power factor lagging means cos theta equals to 0, that is theta equals to 90 degree lagging, right. So for that case R equals to 0, there is no resistance, the resistive part is present at load, so all the impedances are assumed to be a reactance. Okay, so all the load impedance is assumed to be a reactance, load reactance. Okay, so that, right, the load is purely inductive, so that the load is purely inductive, that is IA, that is, as the load is purely inductive, the IA lags behind EF by 90 degree. Okay, so IA lags behind the voltage by 90 degree, and phi A also lags behind EF by 90 degree, and FA also lags EF by angle 90 degree. Okay, and EF all time lags behind FF, that is phi F, by 90 degrees. So that will be the, during this 4 concept, suppose we are taking EF as a reference phasor, so phi F and phi A will be here, phi F and FF will be here, and it, from this it will be again lagging by phi A, IA and FA. Okay, so the resultant one will be, you can see that the flux is demagnetized, this one, right, the flux is demagnetized, this FF and FF, phi F. Okay, so this phi A and phi F are in opposite direction, that means phi A opposes the A phi F, right, that is demagnetization effect, exists, demagnetization effect exists. That means whatever the armature is magnified by acceleration system, which will be demagnetized by loading effect. Okay, so it is undesirable case. This is the undesirable case, as the fluxes are demagnetized, right. So next one, that is case number 4. I will move into the case number 4 now. Case 4, when alternator is at 0 power factor leading, when alternator is connected with 0 power factor leading, that means the load is now leading in nature, having 0 power factor, that is cos theta equals to again 0, but here theta equals to 90 degree leading, right. Previously it was 90 degree lagging, now it is 90 degree leading. Okay, so now write, so EF, so now write, so leading means the load is purely capacitive, the load is Z equals to ZL equals to XC, purely capacitive, and R equals to load resistance equals to 0. The load is purely capacitive. For this type, this, right, phi phi A, IA and phi A will lead EF by 90 degree. IA will lead EF by 90 degree. FA will lead EF by 90 degree. And EF will lag behind the phi F, that is FF, by 90 degrees. So from this concept we can draw that EF and phi F, FF was present previously. So this is 90 degree. This is the inherent characteristics of synchronous generator. And here another phi A will be here, IA will be here, and FA will be here, right? So these three are assist this phi F. That is phi A, FA, IA will assist phi F and FF, okay, to the generator. Okay, so that means for zero power factor leading type of load, it is very much desirable, okay, which is very much desirable. Okay, so now if we summary, that is a case number 1 for case 1. So if we now summarize it, that is for case number 1, no effect of loading. Okay, no effect of loading. So case number 2, that is for the case number 2, it was cross magnetization exists. And case number 3, for case number 3 it was demagnetization exists. And case number 4, that is this case, magnetization exists. So first one no effect, second one cross magnetization, third one demagnetization, and fourth one only magnetization. That is, it assists the field flux, right? It assists the field flux. So these are the four cases for the EMF and flux phasor diagram for an cylindrical pole alternator. And now there is another type of alternator, which is the salient pole type alternator. And for the salient pole type alternator, the phasor and flux EMF will be discussed in later. So today's class up to this much. Okay, thank you.